All right, so our next speaker, she has actually come on the TIPE conference multiple times, sharing her expert knowledge. Her name is Sarah Jordan, CEO of Scald. She's going to be talking about combining the best of both worlds, additive manufacturing, evaporative casting. That's some exciting topic there. So thank you so much, Sarah. And the floor is yours.
Yeah, hopefully I'm doing this right by sharing my screen. All right, bear with me. All right, hopefully you guys can see PowerPoint. All right, well, let's just get started. So, yes, I'm Sarah Jordan, CEO and co-founder of Schooled. In addition to founding my company, and I am also working part-time on finishing out my PhD in manufacturing engineering at Worcester Polytechnic Institute, based on the technology that we are developing here. So, combining the best of both things. So, I decided to ask Chat GPT, because that's like the thing to do these days. What are the best things to combine that are two distinct things? And the AI had some interesting answers on this. And interestingly enough, pretty much most of the things it came up with were food combinations, which I thought was pretty interesting. I mean, how can you go wrong with peanut butter and jelly, or ham and cheese, or all of these delicious foods, right? So I decided I had to be a little bit ask my question a little bit better to get what I really was interested in, like combining manufacturing processes. So I decided to ask it that. What are the best combinations of manufacturing processes, right? So the answer there was a little bit interesting as well. They came up with all kinds of combinations of manufacturing processes. Now, I do think there is a little bit that the AI has some room for improvement. I'm not quite sure what the difference between 3D printing and CNC machining together versus additive and subtractive manufacturing. It didn't quite distinguish those, although in my mind, those are kind of synonymous with each other. And I also thought it was a little bit interesting that it put casting and forging together, when usually those are kind of considered alternative processes. While you may use cast metal that becomes a forging, that's usually a pretty blocky shape and not a net shape like we think of if we're making a casting in my world. But I definitely thought it was interesting, and it does work pretty well. But I just wanted to kind of give you some thoughts on putting things together in new combinations of ways. But I think part of the issue here with the AI is the fact that this is kind of a trick question, because in general, when we're manufacturing things, we don't just use two processes. And really, realistically, if we go back to cooking, that lasagna isn't just pasta and cheese. It is a number of different things. And that's really what also happens in the manufacturing world. We put together, it might be two high-level processes, but then those processes have sub-processes. So I'm going to get into this a little bit with the new hybrid process that we are developing at Schooled, which, as was said, we have named additive manufacturing evaporative casting. That is named after the two parent processes that go into this. Basically, we are 3D printing using polymer 3D printing or additive manufacturing, and putting it together with a process most frequently called lost foam investment casting, but sometimes it's called evaporative casting. Sometimes it's called full mold casting. It has a number of different names. Because we're not using a foam in our process, we didn't want to call it, lost 3D printing. That also is sometimes used with an alternative process where they burn out the 3D print. But in our process, the key thing to keep in mind that's different is that while we do end up burning out the polymer, we do not do that in advance. We actually burn it out by pouring the molten metal directly onto the print, which essentially vaporizes and creates the mold at the same time. And then that then creates the replica part. So I'm going to go into this a little bit more detail, but that's high level what we're doing. So 3D print, vaporize it, get a part. Why would you want to do this? Well, there's a number of different benefits compared to alternatives. It eliminates tooling. Our process has 10 times the accuracy compared to sand printing or traditional sand casting. And it's significantly faster than investment casting. So while our process is technically a type of investment casting, if you compare it to lost wax investment casting, a process that has been around for about 6,000 years, since the Bronze Age, when statues were started being made that way, those processes take 3 to 4 weeks typically of process time, not even counting lead time and all the other wait time, but just like the process itself is very lengthy. And our process can actually be done in less than a day. So benefits there. And then compared to direct 3D printing, significantly more affordable option. So everyone, well, maybe not, but I would imagine most of the people who are at this conference are aware of benefits of additive manufacturing. You've probably heard of a lot of these things. Sometimes there's certain things that are hype or exaggerated, but in general, these things are true, that there are all kinds of impossible shapes. You can reduce inventory, reduce lead time, eliminate tooling, eventually get to, lean ideals of single piece flow. There's this thought that complexity is free. Maybe it's not actually 100% free, but it is significantly more affordable than with traditional manufacturing with huge batches. It can be used for lightweighting and topology optimization, part consolidation. Like, there are a lot of benefits and reason to do additive manufacturing, design constraints, like lots and lots of reasons, right? But metal manufacturing is over a $3 trillion industry globally, and metal additive manufacturing is about 3 billion. So we're talking about a process that so far has only penetrated 0.1% of the total market. And there are reasons that it is, while it's growing dramatically, there are reasons that it has still a pretty tiny market share. So what are the drawbacks of additive manufacturing? There's very costly equipment in most cases. The raw materials are costly. Sometimes labor is costly. A lot of places using 3D printing are relying on engineers, skilled technicians, highly trained people. Post-processing can be quite expensive. And then there's the time of doing that, whether it's hipping, heat treating, EDMing, prints off the build plate. All kinds of things are needed sometimes to get the final end part. Process can be slow, and if you're talking about the context of how much is your build rate per time, in many processes you're talking about a few pounds per day, maybe 20 pounds per day in a lot of cases. Maybe some of the processes like, say, cold spray can get up to like 200, 250 pounds per day, but you're still talking about pounds. You're not talking tons per hour. So it is relatively slow compared to conventional manufacturing. Then there's this trade-off in size and precision. Generally speaking, if you're making much larger parts, you are making ones that have less tolerance control, and then they require even additional post-processing time and cost to get the machine to what the net shape you actually need. There's somewhat limited alloys, although that is definitely expanding. Properties may be unknown in a lot of cases, which requires a lot of data to be obtained in order for people to rely and trust on them. Depending on what you're doing, they may be less predictable. They may be worse. This leads to problems with qualification, and ultimately a lot of, especially for metal additive, it's being used in somewhat limited use cases. Partly because of cost, because the industries that are willing to pay a lot more tend to be in medical, aerospace, and defense. But then those are also tend to be very highly regulated, where this qualification becomes an issue. So while it's growing and there's lots of opportunities and great things about additive, it's also got some issues. So I'm going to go into a little bit here about loss from investment, because I'm guessing most people are not as familiar with this process. So in lost foam, you create a foam pattern. Now, typically this is made by injection molding with a tool. It may also be made by machining. In this case, this example is a irrigation part. This was made with injection molding. Those are assembled by gluing them together in a complex, basically, so you can do a whole bunch all at once. A very thin ceramic coating is applied that is allowed to dry. This is then compacted in ceramic beads so that everything's tightly packed, and then molten metal is poured directly on that foam, which vaporizes, fills in the cavity, and then gives you exact replica part at the end of this process. So essentially our additive process is very similar to this, except that instead of a foam, we are using a 3D print. So what are the benefits of lost foam? So if we compare it to lost wax, I've already said it's significantly faster. It eliminates all of these different process steps, but its tolerances are nearly as good. And if you compare it to sand casting, it has about 10 times better tolerance control. So eliminates machining if you're comparing it to sand casting. Some additional benefits, there is a lot of data showing that it's a greener process for a variety of reasons listed here. And it lets you do all kinds of complicated geometries that would be difficult in other processes. But the problems with lost foam, because it also has problems, very costly equipment, and compared to additive has costly equipment, but a lost foam production line might typically start at about $15 million, so very expensive. The tooling is very expensive. A tool for one part could cost anywhere from $200 to $2 million per part number. That has led so that typically it's only being used in very high volume applications. A lot of times lost foam does require redesigns because if you're going to make use of its capabilities, that can be a problem. And I mentioned this high volumes. And finally, although you can do it with machined foam, machining a foam one by one is also very expensive. In that case, you might be talking several hundred or $1,000 per part just for that foam to be machined. So our motivation in starting Schooled was to eliminate tooling so that we could solve this problem that we directly experienced in the lost foam casting industry. So as I've kind of gone through this process, so essentially what we're doing is we are eliminating the foam and replacing it with a 3D print, which we are currently using printed PLA that is made using FDM, FFF, extrusion-based printers, depending on how you're known of those, but typically simple desktop printers. So what do we know about this process so far? So this process, I would say, is still, for the most part, in its infancy. We have made prototypes and also are working towards getting it to commercialization, but we are still trying to figure out a lot of things. So we know that on the low side, we've gotten down to 1 millimeter fins. You will notice that this casting here on the bottom right is a very rough surface. That is not due to the casting process. We were really rushed in making these artifacts for the Air Force's Advanced Manufacturing Olympics a couple of years ago, and we did not have a lot of time to optimize our printer settings. So that roughness is actually because the 3D print itself was super rough. And so that carries through in the process. It's kind of what you see is what you get. On the other hand, we also know that we can make things quite smooth. Sometimes we'll do things to actually smooth the print. And then in this case with the brass, we've seen as good as 64 roughness. On the upper end, we don't actually know the upper size that we can use this for. What we do know is that we can join the polymers prior to casting them and build up a structure to make a fairly complicated part. So in this case, these were some actual prototypes for the boating industry. These two parts you see here went together to keep gravel out of an aluminum boat intake. So these are pretty large parts, 85 pounds for the upper one. They're made of steel, very large parts with 26 inches and very long, thin pieces put together. So we don't know the upper limit of this, but we do know that in traditional lost foam, parts have been made that are over 25 tons. So really what you're limited in is not the size of the printer, but actually the size of your melting furnace. So I'm going to get into like how AMEC is solving some of these problems that I see in using the individual processes by bringing them together, how we are solving these processes. So with Lost Foam, our goal was to eliminate tooling, and we have done that by using a 3D print. It's pretty straightforward. You don't need tooling anymore. That means you can expand the use of this process beyond just high volume, and be able to do it in these intermediate zones where it's too expensive to machine foams and too expensive to make tooling. But with 3D printing, it also solves a bunch of the other problems that we've seen. So we believe that this is actually going to broaden the use cases to other markets and industries and use cases where current 3D printing technology is just not a great option right now. So I'm going to go into this a little bit more detail. So cost savings. So desktop printers are not expensive. I think most people are aware that, like, on the ultimate low end, you can get them for less than $200, although we typically do buy somewhat better ones than that because we do like some of the bells and whistles they come with. This process also has inexpensive raw materials. So casting has low-cost raw materials, right? Typically scrap material. So we were also recycling things. PLA, also low cost, filament, low cost. Post-processing time and cost is also less because this is a much closer to a net shape process. Typically, we expect around 0.3% precision. So that means that you're eliminating a lot of the post-process machining. And it also, typically, these materials we're doing, we're not hipping them at this point in time. I mean, I suppose that could be something that somebody would want, but typically we're not doing that. In a lot of cases, if we're using, say, A535 aluminum, we actually don't even heat treat them. We just use the material as cast because that's how it obtains its optimum properties. And finally, for scaling, the process of an extrusion printer is not super fast, but because the equipment is affordable, people will tend to have print farms. So you can make it much faster just by buying another, $1,000 printer and just expand that way. So the main bottleneck is actually the melt furnace. Depending on the size of the melt furnace, it's pretty easy to have production rates that are measured in tons per hour. So I have this chart here from Paul Gradle that recently came out, and he shows here that there's this deposition rate versus feature size, but he doesn't actually list extrusion printing on here. So I have taken the liberty in this presentation to add that. So typically the feature size for extrusion printing is about 1 millimeter. And if you have just one desktop printer, that's going to put you at about 10 cc's per hour if you're printing it solid. But we don't actually print it solid. We tend to print this at as little infill as possible. So that actually puts you out farther, which is a little bit more interesting. It's like, okay, you have a feature size that is improved compared to some processes such as this DED process, but still it's not as good as the powder bed fusion with respect to the feature and the deposition rate. But because, as I mentioned, you can have a printer farm, then you can actually push this out farther along this deposition rate. And also, I think you need to consider the fact of what is the deposition rate by equipment, not just by purely the deposition rate. Because if you're going to be doing this with a machine that costs $1 million, that's quite different than if you're doing it with a machine that costs $1,000. So if we push this out with 100 printers, then you can actually see where it starts being quite interesting, because now you can have good feature size and a high deposition rate together. And again, 1,000 printers, even more. And this is a log scale. AMEC alloy capabilities, we are currently, again, exploring this. We've done proof of concept in a wide variety of alloys as shown on the left. We're currently doing R&D with aluminum alloys A356 and A535, with stainless as well as with these 3 Inconel alloys to demonstrate that, and this is currently our hypothesis, so we're trying to get evidence of it, that the resultant material is the same and is equivalent as that produced by traditional casting methods. But we believe a lot more alloys are feasible, some of which we have not cast before. And some metals probably will not be good options in this process. So, as I said, we're working on qualification evidence. The data we have so far does indicate that this is likely going to be the same. We've done some, hardness testings and microstructure, but what we're really working to get is pedigreed tensile and fatigue data, so that we have statistically valid data that people are willing to rely on. So a bunch of research is going on in this area. We're continuing to characterize things, starting to think about computational modeling, starting to look at multi-materials as well. So lots of exciting work going on in the AMEC process currently, as well as in the future. So with that, I will stop sharing, and I am happy to answer any questions.
All right, you have a question here. Which industries are currently actively adopting your technology, and what are their main use cases?
Oh, that's an interesting question. Yeah, so we are definitely talking to people in lots of different industries. So a lot of our current work is in, actually, I would say, the conventional markets that additive has played in. So defense, aerospace, and then other markets there we're starting to make prototypes. I would say athletic gear, automotive, just really a really wide variety of use cases.
Oh, interesting. You said athletic gear. Like, what would be an example of that? That's really cool.
Oh, yeah. So we're working on a project right now for customized football face masks. So this company, they want to make, so face masks are kind of boring. They're all the same shape and they're made by welded wire. So we're working on a project to try to demonstrate our process to be able to make much more interesting designs for that. And this company, their hypothesis is that they believe that ultimately football face masks will be as branded as shoes, which I think is a really interesting idea, that you might have, the Bengals, some kind of tiger logo on the face mask, or Nike swoosh or whatever.
Oh, wow. That sounds interesting. Looking forward to seeing the press releases on that. Today, like, if someone wants to use this technology, where would they work with you, or would they buy the technology from you? Like, how does the whole process work?
Yeah, so right now we are doing things, I guess, kind of in that service center model, prototyping things. We do think down the line we will be selling equipment, licensing technology. But I mean, in general, and this is based on, my experience, where I used to work at Fabrisonic, which is a different 3D printing company, is that generally people don't want to buy equipment until they've, tested it and you've demonstrated that it's good for whatever their use cases are.
Awesome. So are you guys working with any, let's say, universities to explore other applications? Wondering if there are students in here that want to, work with you in some capacity. How would that happen?
Yeah, we currently we do work with Ohio State right now on some projects, and we're in discussions with some other universities. University of Northern Iowa has a big foundry program, Ohio University, and then we also, have interns and things like that. So yeah, definitely lots of opportunities.
Interesting. We have some chats coming in. And so what are the challenges you think you'll have to overcome to bring the technology to new heights?
That's a good question. I think the biggest thing that we are trying to start working on, so right now a lot of this technology is based on our having really deep experience in this very niche casting area of lost foam. So I think for us to be able to sell equipment, we need to develop a computational model so that we can just take in a design and it spits out the settings. So that's definitely where we think things need to go.
Oh, interesting. So to help take the technology to another level is very important, especially when you're building a new machine.
Yeah. So it can't be, we can't scale if it's based on what's in my brain, right? It needs some computers to like tell people what to do.
Are there off-the-shelf technologies that people can leverage today?
Actually, no, which is kind of sad. Like, there's computational modeling in the foundry industry, but not in the parent company of this process. So that's just a gap there that, hey, if somebody's good at multi-physics modeling, I'm interested.
Fantastic. Well, that's about it for the questions here. Are there any other topics you'd like to touch on to share before we close this presentation?
I guess I just think that, I think there's lots of ways to combine additive processes in new and novel combinations. I mean, this is one way to do it, but I'm sure there are lots of them. I know people that like, putting together machining with DED machines and like, I just think there's lots and lots of ways to combine things. That's kind of why I started with the chat, GPT stuff, is because, it's like cooking. There's lots of ways to combine things, and I think people just need to be creative and not just think, oh, it's all been figured out.
That is creative. And the reality is today there's about 9 or so additive manufacturing technologies, but you're saying there's way more out there and we shouldn't stop now. We should continue furthering that.
I mean, at a high level, they might be in these classes like, okay, extrusion, sheet lamination, things like that. But like, then there are processes like cold spray that they don't fit into any of these categories that exist, or they're like my process, they're combinations of things. So
speaking of process, we do have one question coming from Clement. Miss Jordan, as compared to typical lost foam processes, are there any different provisions for escaping pattern gases? Thanks.
That's a good question. What do I want to say there? I would say it's very similar. The gas is still going out the permeable coating wall. It typically is still using a vacuum to suck it off. So I'd say it's fairly similar.
Fantastic. Thanks, Clement, for the question. Well, I guess that is the end of the presentation. Thank you so much, Sarah, for your time. If folks want to find you, what's the best way to do that?
I mean, I will be in and out networking today. If you want to just say hi, you can also like look me up on LinkedIn. I think my name, like, it's under like 3D printing Sarah or something like that. Kind of Sarah Jordan is a super common name, so to try to focus me. I also do have a thing on LinkedIn, Metallurgy Monday. So if you follow me, then you will start learning basic metallurgy.
Oh, what is it called? Milling Monday?
Metallurgy Monday.
Metallurgy Monday. Okay,
Yeah.
everyone, time to follow Sarah Jordan to get your Monday fix. And are you going to be at any of the conferences showing off your technology or your parts so that we can all see this in the spin?
So we'll have a booth at AMUG and then also at the Military AM show, which is next week. Rapid, I'll probably just be walking around. But yeah.
All right. So for those who will be attending those shows, do pass by Sarah's booth and spot her like Waldo at Rapid and TCT.
All right. Thanks, Jen.
Well, thank you everyone for your time today.